So this video contains 4 integrals. Each of these integrals may be calculated using a trigonometric change of variables, and that is because of factors such as this square root here. And what I suggest you do is that you write the integrals down on paper, try to calculate them, and then on the next slide I will write down the answers. And if you have not calculated any of them correctly or are stuck in any of them, you can look later at the video, scroll through to the relevant bit and see what you needed to still master. So with that, I think you should write them down, pause and try and calculate them. So welcome back, and here are the 4 results. This integral is a half x times the square root of 1 minus x squared plus the arcsine of x. That's something which you can check is true by differentiating this side. This definite integral has value a half, and we would expect a positive result because the integrand 1 over 2 minus x squared to the 3 halves is positive. And this integral here has this form, and this integral has this form, all of the 3 indefinite integrals up to integration constants. And again, it's a good exercise here and here to check that these results are correct by differentiating them. If you have all of them correct, that's wonderful, and you can stop here, and if you're stuck on any of them, you can look forward now through the video, scroll through to find the relevant bit, or you can just go back and try to check it again. So with that, I'm going to now move on to the next slide and calculate this first integral. So the first integral is to integrate the square root of 1 minus x squared with respect to x. And we look at this, and this factor here hopefully makes us think about a sign substitution. If there was a factor of x out front, we wouldn't do that. It would be a very easy integral and we could just write the answer down. But here we don't have this and we have to make a substitution. So to help guide us, what I'm going to do is draw a triangle which will help me understand what my change of variables is. So here is a triangle, right angle triangle. Our new variable is going to be u, and we are going to say that the sine of u is equal to x. So here we're going to have x as one side of the triangle, 1 as the hypotenuse, and the square root of 1 minus x squared here. And this is the reason why this is a good change of variables. The square root, which is making this integral difficult, appears very naturally in terms of this angle u. And what we see is that the cosine of u is the square root over 1. So we have that the cosine of u is the square root of 1 minus x squared divided by 1, which I'm not going to bother to write down. We also see, of course, that if the sine of u is x, then u is the arc sine of x, and we also have that dx du is the derivative of sine of u with respect to u, and that is the cosine of u. So all of this information follows from drawing our triangle, and it is also true if the angle is not just between 0 to pi over 2, it's also true for negative angles from minus pi over 2 to minus pi over 2 to 0. This still all holds as well, but I'm not going to go through that argument. It's something you're welcome to go through and check. Now, the formula that we're going to be using, the key formula that we should recall, is that if we are integrating some function of x with respect to x, it is always possible to rewrite x in terms of a new variable, and then we have to insert dx du, and then we can integrate with respect to our new variable. And here we have written x in terms of a new variable, so we can rewrite our integrand, here the square root of 1 minus x squared, in terms of the new variable. So we could say that here we have the square root of 1 minus sine squared u, and that is the square root of cos squared u, and we are entitled, because of the way that the arcsine is defined, to always take the positive root. But I'm not going to go through that in this video, but we are always entitled to take the positive root. So therefore, our integral, the square root of 1 minus x squared with respect to x, is the integral. Now we've said that this square root is the cosine of u. dx du is also the cosine of u, and we integrate with respect to u. So we have the integral of the cosine squared of u with respect to u. And this is an extremely standard familiar integral, the integral of cosine squared. We use the double angle formula to rewrite the cosine squared in a way that we can integrate, and what we say is that the cosine of 2u plus 1 all divided by 2 is the cosine squared of u. And now we have something which is easy to integrate, plus something here, just a half, which is very easy to integrate. So what we get is, let's take out a factor of a half, this factor here on the bottom, and the integral of the cosine of 2u is going to be a half sine of 2u. So if I differentiate this with respect to u, the sine becomes cosine of 2u, and then we multiply by the derivative of 2u, which is 2, which will cancel with the half, so yes, that's correct. That's going to give me the cosine of 2u, plus u, which I get from integrating the 1. Now, at this stage, I might say, well, 2u is 2 times arcsine of x, and we have the sine of 2 times arcsine of x, and that would look really horrible and very complicated and unpleasant. It is much easier if we just think about the double angle formula and just recall that the sine of 2u is 2 sine u cos u. Just trying to squeeze a u in here. So this means that here we have 1/2 open brackets. Now a half sine 2u that we have here, the half and the 2 cancel, so we're left with sine u cos u. Sine u is x, cos u is the square root of 1 minus x squared. So we have x square root 1 minus x squared plus u, and u is arc sine of x, close brackets, and we can add an integration constant. So what we see is that the integral of the square root of 1 minus x squared with respect to x can be rewritten in this way as a half times the square root, or times x times the square root of 1 minus x squared plus arcsine of x, close brackets. And it is possible to check this by differentiating this side with respect to x and seeing that, as expected, you obtain the square root of 1 minus x squared, the original integrand, and that shows that our integral is correct. So the key things that we used here, we saw this square root factor, we didn't see a simple factor of x outside to make it easy, and we thought therefore we were going to use a sign substitution. And the reason that we know that we've made the right substitution is because the sides of the triangle satisfy Pythagoras' theorem, and the nasty factor here is one of the sides of the triangle. And here we've just set up everything that we needed and recall the key formula for making a change of variables, And then when we got to the integral of cos squared, we recalled that if you're integrating cos squared or cos to the fourth or cos to the sixth, you use a double angle formula like this. And at this stage, we thought we want to write this sine of 2u in terms of trigonometric functions of u, here and here, because in that way the answer we're writing is reasonably simple. And with that, I'll stop and move on to the next integral. So the second integral that we want to calculate is a definite integral from 0 to 1 of 1 over the square root of 2 minus x squared all cubed. In other words, 2 minus x squared to the power of 3 halves. And to do this, we recognise that we need to use a sign substitution, and this we could do algebraically, but I think it's easier if we start off by actually drawing a triangle. So let me draw a triangle here. We're going to call this angle U, doesn't matter what we call it, of course. And if we make the right sign substitution, then this factor here of 2 minus x squared is going to naturally appear. So let's assume that we have this, that the side here has length square root of 2 minus x squared. And of course the sides of this right angle triangle have to satisfy Pythagoras' theorem, and if we were to square this we would get 2 minus x squared. So here we would naturally want to write the square root of 2, and here we would naturally write x. So if we look at these sides and just check, the square root of this is 2 minus x squared, the square root of this is x squared, add the two of them together we get 2, and the square of this is 2. So this works. So what we're now going to say is that the sine of u is x divided by the square root of 2. So therefore x is the square root of 2 times sine u. Dx du is the square root of 2 times the cosine of u, and u itself is arcsine of x over the square root of 2, which follows just from this. We take the inverse sine function of both sides and we get this. So now let's recall our key formula. So let's just recall the integral f of x with respect to x is going to be the integral of f of, and now we can rewrite x in terms of some new variable that we've called u. We insert by hand dx du, this is a consequence of the chain rule, and then we integrate with respect to u. So here is our integral, here is everything that we're going to need, and here is our formula. So from this we see that the integral from 0 to 1 dx over 2 minus x squared to the power of 3 halves is going to be the integral. I'll talk about the limits in a moment. Now, what we have here is 1 over 2 minus x squared to the 3 halves. And if we just go back to here for a moment, looking at our triangle, we see that the cosine of u is the square root divided by the square root of 2. So therefore we also have that the cosine of u times the square root of 2 is the square root of 2 minus x squared. So now, going back to our integrand, we have 1 over root 2 cos u all cubed. We insert dx du, which we have here. So that is, let's just put a dotted line here. We insert, let me write it on the top, root 2 cos u. That is the dx du factor. And now we integrate with respect to u. Now this is a definite integral, integrating from 0 to 1. So here we're going to be integrating from x is 0 to x is 1. Now at x is 0, we have u is 0, since u is the arcsine of x over root 2 and arcsine of 0 is 0. And at x is 1, u is the arcsine of 1 over root 2, and that is pi over 4. Sine of pi over 4 is arcsine, sine of pi over 4 is 1 over root 2. So therefore, our integral 0 to 1 dx over 2 minus x squared to the 3 halves is the integral now expressed in terms of u from 0 to pi over 4. And here we have root 2 times cos u. On the bottom we have root 2 cos u cubed. So we have 1 over root 2 cos u all squared. The 1 over root 2 squared is going to give us a factor of a half. And 1 over cos squared is sec squared u integrated with respect to u. So this is 1/2, I can pull it outside the integral, and the integral of sec squared is tan, because the derivative of tan is sec squared. So we have the tangent of u from 0 to pi over 4. So therefore our integral from 0 to 1 dx over 2 minus x squared to the 3 halves is going to be 1/2 times, and now the tangent of pi over 4 is 1, minus the tangent of 0, which is 0, so our answer is 1/2. And our result makes sense in that it is positive, and our integrand here is positive. 1 divided by something to the 3 halves is positive, so that's good. If we want to check it as well a bit more carefully, what we could also do is the following. You can check by writing that the tangent of u, or half the tangent of u, let's not forget the half factor in front, half the tangent of u is, from looking at our triangle here, x over root 2 minus x squared is the tangent, so we have 1/2 x root 2 minus x squared, and we can check this by differentiation. So in other words, if we differentiate this result with respect to x, this is the indefinite integral, we should get 1 over 2 minus x squared to the 3 halves, and that's a good thing to check. And with that, I'll move on to the next integral. So on this slide I want to calculate this integral, and we see here this factor of the square root of 1 plus x squared, which makes the integral look potentially difficult. If there was a single factor of x in the numerator it would be easy, but we have 2 factors. So what we're going to do is to use a tangent substitution, and the reason for that becomes clear if we draw a triangle. So here's our angle u, and because here we have the sum of 2 terms, in the square root, it is very natural to write the hypotenuse of the triangle here as 1 plus x squared. And then if we say here we have x and here we have 1, the sides of the triangle satisfy Pythagoras' theorem. 1 squared plus x squared is the square root of 1 plus x squared, all squared. So the tangent of u is equal to x over 1, or just x is equal to the tangent of u. And dx du, which we'll need in a moment, is sec squared u. And we also have that the cosine of u is 1 over the square root of 1 plus x squared. So the reason why the tangent substitution is natural for integrals such as this is because the square root factor makes it difficult, but the square root factor can be simply written in terms of the cosine of u. The cosine is 1 over the square root factor, and therefore we can hope that perhaps integrating in terms of u is going to be easy. So, or at least not completely difficult. So let's have a look at this. What we have to recall is the following key formula. So we recall that if you have an integral f of x integrated with respect to x, you can always rewrite x in terms of a new variable u, just as we've been doing here, but then you have to insert by hand dx du, and then you can integrate with respect to your new variable u. And this formula follows from the chain rule. So what we see is that our integral I is going to be the integral of x squared, and x squared here is tan squared u, so that's reasonable. And this is divided by the square root, which means it's multiplied by 1 over the square root, so it's multiplied by the cosine of u. And then we have to include a factor of dx du, and we've worked that out already, it's sec squared u. And then we integrate this with respect to our new variable u. And looking at this, we see that the cosine is going to cancel with one of the two powers of sec. So we are left with the integral of tan squared times sec. To calculate this integral, we could use that tan squared is sec squared minus 1, but what I'm going to do in a very related way is to say that this integral is the tangent of u times the tangent of u times the secant of u, integrated with respect to u. So all I've done is I've factorised this, and the reason I've done this is because this product here is the derivative of the secant function. So this is something which we can write as a total derivative, so it's easy to integrate. So let's now just recall the integration by parts formula. The integral of f g dash with respect to u is f g minus the integral. Now we swap around which one is differentiated, f dash g, integrated with respect to u. And we are going to say that the function that we are going to integrate is this one because it is a derivative of something. So that means that g dash is tan u sec u. So g dash is tan u sec u, which means that g is just sec u, and f is going to be what was left in the original integrand, and that's tan u. And that means that the derivative of f is sec squared u. So now we can put all of these ingredients into this formula to calculate this integral. So therefore I is going to be f times g, so that's tan u sec u, minus the integral of f dash sec squared u times g, which is sec u, integrated with respect to u. To calculate this integral, what we're going to do is to rewrite sec squared as tan squared plus 1. So what we have is that our integral is tan u sec u minus the integral, open brackets, so it's tan squared u sec u, so that's the tan squared from here times sec, plus, and now we have the 1 from the sec squared times sec, so that's just plus sec of u integrated with respect to u. So we've taken our integral and we've written it as the sum of two integrals, and this is a standard integral, the integral of sec, and this we recognise as being our initial integral, the integral of tan squared times sec. So this is actually what we've been calling I. So what we see is that I is tan u sec u minus I, and then the minus sign here multiplies this and this, so it is minus, and it's the integral of sec, and the integral of sec is the logarithm modulus sec u plus tan u, close the modulus. So now we can take the original integral over to here, and we get our result that twice the original integral is that minus this logarithm. So therefore our integral, our integral is 1/2, and that's just because we had here that 2I is equal to this minus this, so that's when we just divide it by 2. I is 1/2 tan u sec u minus log mod sec u plus tan of u. And now, just looking back at our triangle, we recognise how to write these functions, and I'll also put in the factor of a half that should be here. So this is 1/2 x times the square root of 1 plus x squared, that's the second function, minus 1/2, just trying to squeeze it in here, the logarithm of the modulus of x plus the square root of 1 plus x squared, close the modulus, that's a squared. So what we've got here is tangent times sec, tangent is x, sec is the square root, so that's tangent times sec, tangent plus sec is x plus that. And this is our answer for the integral, and it would be a good thing to do to check that this is correct by differentiating everything here and seeing that we indeed obtain x squared over the square root of 1 plus x squared. But with that, I'll move on to the next integral. So on this slide I want to calculate this integral, and the thing that makes it difficult is the square root. We notice the plus sign, and therefore we think that we might be able to get this through a tangent substitution. So let's just draw an appropriate right angle triangle, and we want one of the sides of the triangle to involve the square root, and because of the plus sign it is again going to be a tangent substitution, we want it to be the hypotenuse, and it's got to be 4 plus 9x squared square root thereof. So that is the hypotenuse of the triangle. This angle is going to be called u, and now we want to write the other two sides of the triangle in such a way that they satisfy Pythagoras' theorem, and that this side 4 plus 9x squared naturally emerges. So to do that, I'm going to put a factor of 3x down as the length of this side of the triangle, because 3x squared is 9x squared. 3x all squared is 9x squared. And here I'm going to put 2, because 2 squared is 4. And this satisfies Pythagoras' theorem, and it involves this factor here. So what we see is that the tangent of u is 3x over 2, so x is 2/3 tangent of u, so dx du, which we will need in a moment, is 2/3 sec squared u. And let's now recall the key formula that we are using here. So we recall that the integral f of x integrated with respect to x can be rewritten as the integral of f of x written in terms of a new variable that I'm calling u, insert by hand dx du, and then integrate that with respect to u. And this formula follows from the chain rule. So our integral here that we're trying to calculate, the integral of 1 over the square root of 4 plus 9x squared, integrated with respect to x, is going to be, well, if we look at our triangle, 2 over the square root is the cosine of u, so I can write 1 over the square root as a half times the cosine of u. And I now have to insert by hand dx du, and that we've already worked out to be 2/3 sec squared u. So this is times 2/3 sec squared u, and now we integrate with respect to our nice new variable. So we have here some factors that cancel immediately. So we see that the half and the 2 will cancel, and we also see that the cosine and one of the 2 powers of secant will cancel as well. So we are left with that our integral is 1/3, that I will put outside because it multiplies everything, sec of u integrated with respect to u. And that is a standard integral, so it is 1/3 log modulus sec of u plus tan of u, close modulus, and we can rewrite this in terms of our original variable x just by looking at the triangle. So sec is 4 square root of 4 plus 9x squared all over 2 plus tangent, which is 3x all over 2, end modulus plus an integration constant. And we can simplify this ever so slightly if we realize that here everything is divided by 2, so we can take out this factor and say that the log of something divided by 2 is the log of something minus the log of 2. So we would have 1/3 minus 1/3 times the log of 2, which is just a constant that could be absorbed into our unknown integration constant. So what we see is that all in all, we can write our integral 1 over square root of 4 plus 9x squared integrated with respect to x to be 1/3 logarithm modulus, and I'm going to write the 3x in front, plus the square root of 4 plus 9 x squared, all in the square root, close the modulus, plus an integration constant. And that is our final result for the integral. And what you can do, of course, and I strongly encourage you to do it, is to differentiate this side and see that you do indeed recover the original integrand. So, in this integral we had some numbers here that were not just ones, and it's important when we draw a triangle like this to ensure that we actually have the square root with the appropriate numbers naturally occurring here. And that's a simple way of making sure that we set up the correct substitution, that x is 2/3 times the tangent of u. And after that, everything progresses very much as before. And with that, I will stop this entire video.